Welcome to another exercise on the simplex algorithm. Here we have a simple exercise of just using the simplex to calculate the optimal solution of the following linear problem. So we have a maximization problem with this objective function. So it means we are going to have two decision variables, x1 and x2. Then we have three constraints as well we need to observe. The first one, 2x1 plus 3x2 smaller or equal to 120. 4x1 plus 3x2 smaller or equal to 150. And finally, x1 plus x2 larger or equal to 40. Well, so much for the problem as such. This is topped off with our so-called non-negativity constraints, so that both decision variables need to be 0 or larger. Well, how to solve this? We first need to get this into a working table. That's what I'm going to do here in this slide. So I copied the problem. Then I'm going to generate a table in the following way. For each decision variable, I'm going to make one column. So I have a x1, x2 column. I'm going to add in the first row the objective function. And then I'm going to add one row per constraint. So x3 represents the first constraint, x4 the second, and x5 the third. So much for the structure. So how to get our values into the table? We're going to start with the objective function. Since it's a maximization problem, what we're going to do is we take the coefficients here of the objective function, but as it's maximization, we're going to multiply them with -1. So we're going to use -4 and -5 here. Since x1 and x2 are up here, they have a value of 0. So we're going to insert 0 and 0 into the objective function and get as a result 0, which we put here on the right side of the objective function. Then for each of the constraints, we have to reform them that they always read like the first two as smaller or equal to constraints. So those two is no problem, but for the third one we need to make some adjustments. Or in other words, we're simply going to multiply the third constraint with -1, which will turn this inequality sign around. So we have -x1 minus x2 smaller or equal to -40. Well, then we are prepared by simply going with taking all the coefficients in front of x1, so 2, 4, -1, put them in the x1 column, take all the coefficients in front of the x2, 3, 3, -1, put them in the x2 column, and take all the values from the right side and put them in the right-hand side values. So 120, 150, and -40. This gives us the first table to work with. With this table, we need to check whether this solution which this table represents is feasible. Feasible means that on the right-hand side, we only have positive values or zeros. Well, the first two, there's no problem, but with the third one, this is negative. So we have to fix this problem before we can start with the actual simplex. So how do we approach this? Well, if there's something negative here, we select the largest negative row as new pivot row. Well, there's only one row with a negative value, so this x5 row will become pivot row. And then from the elements, we're going to observe only those elements which are negative. So those two qualify. Of those two, we compare them with the values up here. Or in other words, we divide the values from the objective function row with these elements. So we get 5 and 4. Then we select as pivot column this column where this quotient is as large as possible. So here we're going to go with x2 as pivot column. So x2 pivot column, x5 pivot row gives us a pivot element of -1. With this, we're going to do our simplex retransformation, which leads to this table. What did we do? First, we switched the variables in pivot row and column. So x5 here, x2 here. For the pivot element, we write 1 divided by pivot element. So it stays the same since it's -1. The other values in pivot row are divided by the pivot element. So -1 divided by -1, -40 divided by -1. For all the other values in the pivot column, we divide them by minus the pivot element. So -1 gives 1. So this column stays the same. So far, so good. We still have these 3 and these ones. For this, we're going to use some rectangle scheme. What do I mean by this? Well, if we want to change this 150, we can consider the 150 as one corner of a rectangle and the pivot element as the opposing corner. Then would be this rectangle, and we recalculate the values by taking this one minus this corner times that corner divided by pivot element. So in our case, we would go with 150 minus 3 times -40 divided by -1. So we have minus, 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 3 minuses, 2 cancel each other out. So we have 150 minus 3 times 40, so minus 120, giving us the 30. For this 120, we go 120 minus 3 times -40 divided by -1. Again, 3 minuses, so 120 minus 120 gives us 0. This we are going to do for all the remaining values. For the 0 here, we have this rectangle, so 0 minus this times this divided by this. For this 4, we have this rectangle, so 4 minus this times this divided by this. For this 2, this rectangle, and for this 4, that rectangle. This gives us this new table. We see on the right-hand side, all the values are positive or 0, so our solution is feasible. This means we can start the normal simplex algorithm. For this algorithm, we're going to take a look at the row of the objective function, especially those values. And we select a column. We select a column with a negative value in the objective function row. And ideally, we select a column with the absolutely largest negative value. Well, here it's quite easy. There's only a single column with a negative value. So x5 becomes pivot column. And for the pivot row, we consider the positive elements in this column. So those 3. And we divide the right-hand side by the values. So we get 0 by 3 is 0, 30 by 3 is 10. And we select the row with the smallest result. So we select here x3 as the result. So pivot row, pivot column gives us this 3 as pivot element. So on the next slide, we can do our simplex recalculation for this 3. So I copy it here, do the recalculation. First, I switch variables in pivot row and column. Then for pivot element, I go with 1 divided by the pivot element. Everything in pivot row is divided by the pivot element. So -1 divided by 3, 0 divided by 3. And everything in pivot column is divided by -3 by minus the pivot element. So minus minus gives plus 5/3, -1, and plus 1/3. Now we can do the rectangle scheme again. However, since we see there is a 0 in pivot row, this makes our job a bit easier, because if there's a 0 in pivot row, we can just copy the respective column in which the 0 stands. So we can just copy this column and put it here. So this simplifies our work a little bit. And then For the other values, however, those two, that one, we have to do the recalculations. So if we work with this 1, we have 1 minus this times this divided by this. So minus, minus, minus gives 3 minuses. So we have two of them cancel each other out, remains 1. So 1 minus 5/3. 3/3 minus 5/3 is minus 2/3. So this value is negative, so we are not yet finished, because as long as there are negative values in the objective function row, we are not at the optimal solution yet. So we have to calculate those two as well. Well, for this one, we're going to use this rectangle. So 1 minus minus 1 times 3 divided by 3. And for this rectangle, so this minus this times this divided by this, giving us this one. Well, this is the new table. So for this column, which is still not positive here in the objective function row, we have to select a new pivot element. Well, this is negative, the only negative element, so this x1 becomes the new pivot column. We consider all the positive values here, positive elements, so 2 or 2/3 are possible pivot elements. We divide right-hand side by these elements. 30 by 2 is 15. 40 by 2/3 is 60. So this one, this row, delivers the smaller result. So 2 becomes our new pivot element. Again, I'm going to switch to the next slide to do the transformation. So I do all the calculation again for this 2. Switch the two variables, divide 1 by the pivot element, divide everything in pivot row by the pivot element, and for the pivot column, divide everything by minus pivot element. Well, since I have done quite some calculations, the first thing I'm going to check is this value here, because if this is positive, I know I'm at the optimal solution. So I consider this rectangle, so this minus this times this divided by this. Minus, 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 3 minuses, so 1 remains. So 5/3 minus 2/3 divided by 2, so minus 1/3 gives 4/3. So this is positive. So both entries in the objective function are positive, meaning I do not have to calculate these two values here because I will not need them. Here I still did this, but for completion's sake, but you would not necessarily have to do this. You would only have to calculate the value here and the value here, because x2 is one of the two decision variables, and this one is the value for the objective function. So for this one, we consider this rectangle. So 40 minus 30 times 2/3 divided by 2. And for the 200, we use this rectangle. So 200 minus this times this divided by this gives 210. Well, as I said, this is the optimal solution. We see this since all of these two values are positive. It's feasible. And well, once it is feasible and we use Simplex, it will always remain feasible. And we have one small way to check whether we did our calculations correctly by taking a look here at the objective function value. Because whenever we do the Simplex recalculation, not when making it feasible, but when doing the Simplex recalculation, then this value will always increase or at least stay the same, but it will never decrease. So that's a good indicator whether we did our calculations halfway correctly. Well, as I said, that's our optimal solution. So all the variables up here have a value of 0. All the values here have the values from the right-hand side. So our optimal solution is 1530 with an objective function value of 210. Well, that's about it then for this exercise. So I say goodbye and see you next time.